So let's talk about weak and strong bases. So these are going to raise the pH, and similar to weak and strong acids, this is not based on how much they raise the pH. A strong base isn't like one that shoots it directly to 14. That the pH is based on concentration. Weak and strong is how well this completely dissociates in water. So a strong base will completely disassociate in water. So here's the general equation that you probably see in class. B is for base. H2O, that's our water, and we see it separating, and I color coded this to show you how the water splits. One of these hydrogens is going to be attached to the base, because remember, it's in this example, the water is going to be the acid, and the B is going to be the base, so water is a proton donor here, so it's going to donate its proton to the base. And then the other part that's left after this, so when we take H2O, just going to draw it out real quick, which looks something like this. This is not the actual structure. This is just so you can see what's bonded to what. This part comes off, OH is left. So that part's going to go there, this part goes there. The plus and the minus cancel out. So here's our proton that's donated. If we get rid of a plus here, we're going to have a minus charge there. You should also recognize from all your work with the polyatomic ions that this OH minus on the end here, this is hydroxide. This is the polyatomic ion hydroxide, and that's going to be really important. Okay, so just like with the weak and strong acids, the strong base is going to have 100% dissociation, 100% of it will become products. In weak, it's the same thing, but the arrow goes both ways because not 100% goes to products, and some percentage will go there, and this is based on the pKb, which we are not discussing in this video. So that's our difference between weak and strong. Strong is 100% dissociation. Weak, not 100% dissociation. So now let's talk about how can you tell what is a strong base. So our strong bases are going to have the form metal plus hydroxide, OH. So let's list some, and this is not going to be inclusive. Sodium hydroxide is definitely going to be a strong base. Magnesium hydroxide. Magnesium has a charge of 2+. Hydroxide has a charge of -1. When we flip those charges, we get this formula. Aluminum hydroxide. Oops, I almost wrote a 2 there. Aluminum has a charge of 3+. So when we balance this out, right in the formula, and flip those charges, that's what we're going to get there. So those are just some examples. There's plenty other metals on the periodic table that you can do, but you can see that the pattern is that they all have the OH, the metal, at the end, the hydroxide at the end, metal at the beginning. Metal cations are always listed first. So that's what we're going to do. So now let's practice this. So go ahead and pause the video for a second. Figure out if these are weak or strong bases and why. Okay, so our first one, we've got potassium hydroxide. So we see that this is our metal. This is our OH, so that's what's going to make that a strong base. Oh, this is going to be the death of me. Okay, next one, NH3, definitely a base. This one is going to be a weak base. W for weak. Because we do not see the formula metal hydroxide, this is NH3, and there's a lot of weak bases that are based on ammonia. It's a really that's what this one is. It's a really common weak base. NH4OH, even though we see the hydroxide here, what's in front of it is a polyatomic ion, not a metal, so this one is going to be weak. And last one, we see that formula metal hydroxide. This one is going to be strong. Calcium hydroxide there. I can do dots, but not lines. Okay, so I hope this has been helpful. Thank you for paying attention.